The modern enterprise is locked in an arms race to acquire accelerators. Organizations hoard hardware, assuming possessing chips guarantees their ability to deploy artificial intelligence. This animated gauge illustrates a common trap, measuring AI readiness by looking strictly at theoretical flops and maximum clock speeds. An isolated benchmark tells you what a chip can do in a vacuum, but any failure in the surrounding architecture immediately strands the processor. Evaluating capabilities strictly by chip generation is a failure of systems engineering. It ignores the physical and digital realities required to keep that processor fed with data. The GPU is not the AI factory. It is a highly capable parallel math engine. It is one critical machine sitting on a much larger factory floor. This diagram outlines the actual AI factory. It is a strict, interconnected dependency chain. It requires physical facilities, compute, memory, network fabric, data pipelines, and orchestration software to function at scale. Because this relies on sequential dependencies, a bottleneck at any single layer will instantly transform a $30,000 piece of silicon into a stranded, underutilized asset. To see how this factory operates in practice, consider a standard enterprise request. A manager asks the system, which distribution center is most likely to miss its SLA this week, and why? Pressing enter on that prompt does not send the question directly to a GPU for math. Instead, it initiates a complex production run. This flowchart tracks the initial path of the prompt. Before any inference occurs, the system routes the request through a security gateway to verify the user's identity and determine their specific data access permissions. Once authorized, the Retrieval Augmented Generation, or RAG, pipeline takes over. It scans the operational data silos, extracts the relevant inventory and labor metrics, and appends this context to the original prompt. The completed payload is then sliced into uniform text units, called tokens, and routed through a software switchyard to locate the specific model tier appropriate for this workload. The math engine is completely dependent on this input pipeline. The fastest processor on the market cannot generate a trustworthy business outcome if the retrieval system fails to deliver the right context. Scaling this architecture quickly collides with physical bedrock. A company can secure executive approval, budget, and hardware delivery dates, only to realize the servers will arrive months before the site can provide electricity. This scale comparison highlights the shift in facility requirements. Traditional IT capacity is planned in kilowatts per rack. High-density AI capacity is measured in megawatts per room. Delivering that volume of power requires massive upstream infrastructure. The data center needs high-voltage utility interconnects, dedicated substations, commercial transformers, and heavy-duty switchgear just to bring the electricity to the building. The lead times for these physical electrical components span years. It is the procurement of transformers, not the availability of GPUs, that dictates the actual deployment schedule. Furthermore, the facility's redundancy models must match the primary load. Diesel generators and uninterruptible power supplies have to be drastically upsized to protect operations from grid fluctuations. Hardware budgets and procurement victories mean nothing if the site lacks the physical megawatt capacity to energize the racks. Power consumption creates a secondary, unavoidable law of physics. Every watt of electricity that enters the compute load must be actively extracted as heat. Modern AI clusters concentrate immense power into extremely small footprints. This density completely overwhelms traditional air-cooled HVAC systems, which simply cannot push enough chilled air to offset the thermal load. This rack cross-section demonstrates the shift to transitional cooling. As airflow stalls, facilities install rear-door heat exchangers, routing chilled liquid directly to the rack boundary. For highest density, ambient air is bypassed. Coolant units pump liquid through loops attached directly to the chips. Once power and cooling are solved, the focus shifts to the internal architecture of the single AI server node. This schematic visualizes the node as a complete manufacturing cell. The CPU acts as production coordinator, while local SSDs hold inventory, like neural network weights. Adjacent to the GPU core, high-bandwidth memory modules pulse, keeping critical data physically close to the math engine. The entire cell relies on a strict integration layer. Motherboards, specialized firmware, power supplies, and network interface cards must bridge these components together seamlessly. This exposes the primary bottleneck in modern inference, the memory wall. Compute cores operate at blinding speeds, but they will sit completely idle if data cannot move from the staging memory into the processor quickly enough. Buying the most capable chip on the market yields no advantage if the surrounding motherboard and memory architecture lack the bandwidth to feed it. Understanding how memory bandwidth throttles performance requires looking at the mechanics of inference itself. It is not one generic action. It consists of two radically different phases. This timeline breaks down the workload. In the first phase, known as prefill, the GPU ingests the prompt and retrieved documents simultaneously, causing a massive spike in compute utilization. Processing this input creates the KV cache, the system's temporary working memory. Then the timeline shifts into the decode phase. The system begins generating the answer sequentially, one token at a time. During decode, the processor must constantly recall the entire model's weights and the specific KV cache to calculate every individual word. This phase is heavily bottlenecked by memory bandwidth, not raw math capability. Every new concurrent user requires their own KV cache. As traffic scales, the pressure on memory capacity multiplies rapidly, threatening to exhaust the system's staging area. Because long documents stress the prefill compute phase and high concurrency exhaust the decode memory phase, abstract benchmark scores consistently fail to predict how a cluster will handle real-world user traffic. When user demand and context lengths outgrow the memory limits of a single node, the platform must become a distributed system. Splitting a single workload across multiple racks introduces the network fabric. This fabric serves as the nervous system, tasked with keeping distributed cores perfectly synchronized. Scale-up connections inside a server node benefit from extremely tight physical coupling. Scale-out connections require data to travel across the room, passing through switches and optical cables. If the network topology is poorly designed, congestion builds. Oversubscribed switches or faulty optical transceivers cause severe microsecond delays during data handoffs between racks. Without precise telemetry and rigorous error handling built into the network layer, operators are completely blind to these brief, destructive stalls. If communication across the fabric stutters, entire clusters of expensive accelerators wait in idle mode for the data packets to arrive. Network topology is a direct throttle on compute efficiency. The final layer governing efficiency is the software stack. Serving engines and orchestration platforms, like vLLM or Kubernetes, act as the invisible managers of the factory floor. Hardware design dictates the theoretical ceiling of your capacity. Software logic determines exactly how much of that capacity translates into useful work. Advanced serving engines optimize economics by grouping hundreds of concurrent requests into dense batches, ensuring the processors are constantly supplied with math and never sit idle. Software also executes techniques like quantization, which lowers the numerical precision of the model. This drastically reduces the memory footprint and accelerates token generation without sacrificing the quality of the output. An immature software stack will cripple a technically perfect hardware platform. Orchestration is the true driver of inference economics. This completes the true dependency chain. An AI factory requires electricity converting to compute, constrained by cooling, bounded by memory, tied by networks, fed by data, and managed by software. Standard evaluations use basic infrastructure metrics, like tokens per second or GPU utilization. But tokens are just manufacturing units. The metrics validating the investment light up on the right: cost per task, labor hours saved, and risk reduced. Before purchasing a systemic supply chain, the enterprise buys outcomes, not tokens.